Let's sum a finite geometric sequence.
Okay, geometric sequence. So the other type of sequence, this formula is a little more complicated, and we only have one.
You might even need a calculator with this one because sometimes...
Well, it's just annoying to do the math yourself, even if it is possible to do it. Sometimes it's like, ooh, that's super difficult. I can't do that. But even whenever it's not that bad, it's annoying to have to do. So feel free to have your calculator handy. You do have to have the first term, the common ratio, and the number of terms. You don't have to know the last term in this case.
But you gotta have some of that basic information, which we are given in our problem. Right. So find the sum of the geometric sequence.
Now this could be tricky with the dots, but we'll actually see that they helped us out. So
what?
Go ahead.
They helped us?
They helped us.
Okay, so if I go to from 4, okay, first term is, so A1 is 4. So we've got that guy all sorted out, no problem. Now I just need R.
Okay. I'm multiplying
by, looks like from 4 to negative 4/3, I'm going to say R is negative 1/3.
I feel like I may have put a typo in there.
Because
I skipped a term.
This should be plus, right?
No, I think I skipped a term. I think there should be a 4/9.
Oh, yeah. There should be a 4/9 in there. So plus 4/9. And then minus 4/27.
Yeah, sorry about that, guys.
That's okay. So we've got this set up, and hey, look, I've got 2 of the 3 pieces. The third piece is right there. So n is 10. Okay,
so if we go ahead.
Okay, so what I'm going to do is just plug these bad boys into the formula that I was given, which would give us 4 times 1 minus negative 1/3 to the 10th power all over 1 minus 1/3. Now, I know this looks really, really strange and wacky, but it actually will sum up what's going on right here. It'll sum up those 10 terms. So as soon as Mrs. K. Steve, this is usually me. We're backwards right now, so we're both in uncomfortable territory.
This is super uncomfortable.
That's really interesting. So okay, so 118,096 divided by 19683.
Yes. Or if you change that to a decimal, you would get something that rounds up to 6 pretty nicely.
5.9999.
I mean, 989.
So almost rounds up to 6 there.
That's interesting. So even though we added a whole bunch of things together and we started at 4, we were only getting to 6. Huh. I wonder what would happen if we kept adding things to it.
I don't know. Well, can we just try real quick what it might be if we just put 100 terms in, just for kicks and giggles?
I'll just go up in
Let's
here.
keep all of this the same, and now let's, instead of doing 10, let's do 100. So it would be the same setup.
Just changing the 10 to 100. Wow, that's a crazy looking fraction there, but
holy jeez.
Now on my Inspire here, it just literally rounded that up to 6. It thinks that if you put in 100 there for that exponent, it thinks this is 6. So that's what we're about to talk about in the next slide, is that we have these series sometimes or we can have a series, something that goes infinitely many terms, and we can add them up and get an actual number. So
I'm excited to see what that's going to look like.
Me too.